No? Yes.
All right. Good morning, everyone. It's my pleasure to introduce for this morning's session Peng-Jie Wong from the National Yat-sen University, who will talk about the eighth and shifted moments of the Riemann zeta function.
Okay, thanks for the introduction. It's my great honor to be here to see all my teachers, friends, and math family member. And probably I should bonjour. And so today I will talk about the S moment and the shifting moments of the Riemann zeta function. And there is a joint work with Nathan in the, well, he's now in the University of Bridge and the transition in Shandong University. And then my body is so confused right now. So if I, during my talk, I say something stupid, please correct me. And so let us start. So let us start with pretty wild, pretty general concept of the moments of arrow function. So we consider subclass of the Separate class, and we use this LSF to denote the arrow function. So that means that we have a Dirichlet series and the Euler product, and they satisfy the functional equation extend to metamorphically to whole complex plane with possible pole at 0 and 1 and so on and so forth. And the typical question is that if we take absolute value and then write the power, and then we want to study this integral. So it looks like if you are coming from the analysis, it's a natural question. You say, okay, we have the function, we want to know the integral. And but on the other hand, in the number theory, this one is close related to the so-called Lindelof hypothesis. So if we can know something about these two, in fact, all of them, and then we have some knowledge for the Lindelof hypothesis. And on the other hand, there's another side of the dual of this question is called a discrete moment. So we are really running over this subfamily of the Separate class. And then you can do whatever you want. You take an absolute value, write the power to the k, or take a derivative to the k. And most of the time, and today I will say some few words that is the most profound example apart from the Dirichlet arrow function is that we consider the holomorphic hospital new form, and then most of the time rising from the elliptic curves, and we consider the quadratic twist, and we would like to know about the information about these two. And why we care, this one is we probably will cite the most famous work in this area, is Murty, they prove that, okay, there's a slightly the departure from these two, the notation, but basically it's this arrow prime D1 is without normalization, you can normalize to have the similar thing for like, basically it's corresponding to this one up to the normalization. And why we care is that by the famous work of Zagier, Kolivagen, and so on and so forth, if you can show that one of them, this length is non-managed, and we have some knowledge for the BSD. So in this direction, what the brilliant idea is that we consider all of them, and we the Professor Murty and Professor Murty, they show that they emit asymptotic. So there's at least one of them, and many of them will not manage. So today, in my talk, I was planning to completely avoid the terminology from the long-length program and the algebraic number theory. I will just focus on our baby or grand example for the arrow function is a Riemann zeta function. So everything is so-called trivial. It's a trivial automorphic form and a trivial arctic arrow function. Everything is trivial here, and then you put everything to be one. And there is a super nice Dirichlet series and Euler product. And there is converged absolutely on the right half plane, and you can extend it to the minimum function over C, which only simplify at S equal to 1. And before the Riemann abandoned the number theory, in fact, he tried to calculate, well, by the way, everyone knows that, I believe everyone in this room knows that Riemann used this one to prove the super famous prime number theorem, and it was completed by the Alderman de la Vallée-Poisson. And before the Riemann abandoned this area, in fact, he calculated several zeros for this zeta function. And he said probably this almost all zeros should lie in the critical line, half line. And then, well, you know, back to later, it's like the pretty naive, innocent questions. We only care about the zeros of the certain holomorphic function. And then even back to the time of the Hilbert, he thought that, okay, this one should be easy, comparing to another two famous questions, including the Fermat theorem. It should be done among his time or right he passed away. And it turns out that from the point of view of nowadays, it's not the case. It's that at least from the point of view for the function field or finite field analoga. This one is in fact the list zeros, they are coming from, they are corresponding to certain geometric structure. And for this one, this one is so the one guess due to the Allen cone is that use the non-commutative geometry, or probably there's a random matrices and so on and so forth. And so these things are even beyond the scope of our analytic method. So instead, we should consider something relatively easier. Is that we consider growth rate, and most of the time it's quite useful in the study of number theory. So the strongest form for this one is Lindelof hypothesis, a point-wise bound. Namely, over the critical line, this growth rate is arbitrarily slower than the polynomial growth. It's at least at most here, the 1 plus t to the epsilon for arbitrary epsilon. And this one in fact shed a light to study the continuous moment of the OL function, because if we consider two-case moment, in fact one can show that this Lindelof hypothesis, this point-wise bound, usually you can see somewhat, you might guess that this point-wise bound might be also hard, because if you have the point-wise bound, if you put your hand to do this complex analysis, usually it's hard. But luckily enough is that if you can say something, you take an average, you forget or you try to overlook all extreme values, and you sort of the upper bound to the t to the 1 plus epsilon, and the Lindelof hypothesis will follow. So this will give at least some hope to say probably this Lindelof hypothesis is doable in some sense. Also, there's a work over we will mention pretty soon, is Hardy, Littlewood, and Ingen. Okay. So, there's a talk in fact I am pretty new to this area of moments. So in fact, this talk is also my note is understanding why people were guessing these things, or there's a convincing evidence to show why we believe this bound. So one thing probably is we can use the Selberg simple spatial limit theorem. Is that if we consider the absolute value of the zeta, take a log, and divided by the half log t, and this one, this probability distribution will like this thing. And for expert, this one means that this inner term, this sum, that behaves like the standard normal distribution with the mean zero and the univariance. And in fact, Selberg showed that if you get rid of this absolute value, you will get a two-dimensional normal. It's a pretty fantastic result. And what Roosevelt and Sandor is that Selberg used a certain complicated zero density estimate to have this one. So the Roosevelt and Sandor, they basically completely avoid this complicated zero density estimate. Instead, they control the corresponding Dirichlet polynomial nicely to get this result. Okay, so with this theorem in mind, after a moment of reflection, and one will know that you can see, because you know that if you regard this one as a random variable, you know that this one is a probability. This one is probability distribution function. So you can do the standard probability theory, assuming that this one is uniformly true for all t. So you can see that you do some integral, it's like a t, you raise the power to the 2k, and to the inside is like half times 2k log t, and you will get something like a log t to the 2k, and you take exponentially, and you will see that, okay, this one, typically, and you take an integration, and you will guess, one will guess that as what I know is that you will see that this growth rate for the even moment is like the t times the log t to the k squared something. And in fact, that is the case, basically. It is due to the famous work of the Sandor. He, based on the one famous identity of the Selberg, he proved the upper bound is basically what we expected, apart from this teeny tiny epsilon factor. And 4 years later, Harper showed that one can remove this epsilon factor. Okay, so you can see we are doing the analysis. Next question, can we do better? We can do better or better, because we will overlook the extreme value. So the answer, fortunately or not, is no, we cannot. Because the Roosevelt and the Hipps and even including some work of the Hissy Brown and many people that the lower bound basically this one is the correct bound. It's a lower bound is also greater than t log t to the k squared. So you can see this IAT is 2k moment is about the size t log t to the k squared. So next we are doing the analysis is that how about asymptotic? If it is asymptotic or not. So it's back to, so there was a wonderful talk about the Hughes data. These two results were mentioned. It's Hardy little and the Ingen, they proved the second moment and fourth moment. And in fact, the Ingen, around that time, he also gave the error term for the Hardy little result. So nowadays, I just mentioned some results about what they can prove the second moment can with the asymptotic and the error like 1/3, smaller than 1/3. And if the Motohashi, they can prove like the 2/3. Okay. So you can see that it's pretty like a century ago. So you might ask, how about, as you can see, this is like if we were like in the position of Hubert, we might guess around the 20th century, we will know the 6 and 8 and so on and so forth. So we will know everything before this 21st century. So that's also not the case, unfortunately, because it's even hard to guess what should the asymptotic looks like. There's a natural arithmetic way to see that they should have the k squared factorial, ak looks like this. So you can grinding this thing, and apart from the one magical gk, as in general, it's just was pretty hard or difficult to prove this one. Although we know the G1, G2 is due to the Hardy and Ditto Ingen. So yeah, before the list works. So this, so even you can say that you can revise it. In fact, this was very difficult. It's not the case right now. So before this Gaussian Corey-Garner result, and it's in fact pretty hard to guess what should one have to this GK. The reason is that we don't know the arithmetic for this GK. And so the first, the people doing here is they are trying to use a standard or the number theory hypothesis. And with some, we will see some, at some points, identify the sum, and we try to break down to the calculating a long Dirichlet polynomial. And then they figure out the correct constant is 42 and it's 24024. Unfortunately, is that their method, although they can produce a mention, they don't control, they couldn't control the error term. And the error term, you can see, we are doing these are all, like I said by Professor Matti many times, it's all about control error. So for these two, they are the conjectures because we don't know if the error is really smaller than these two quantity. Okay. And as mentioned by Professor Matti, it's nowadays not a folklore, in fact, it's a formal conjecture. It's due to the first thing is due to the killing of snots. They use a random measure model. It's based on the work. You can go back to the work of the Montgomery-Dyson. It's about the distribution of these zeros. So if you believe the distribution of a zero is corresponding to the eigenvalues of the random matrices, and then you can produce this corresponding result to do this two-case moment. So they gave the formula. And also there is even something stronger is by these people like 7 years later. They can use a recipe method so they can produce all the lower term and with the last term is t to the half. And also there is another way to get the correct GK is by the work of the Konogov and the Hofstein. In fact, their method is also pretty interesting that in fact they show that their method was capable to deal with the false moment. And then mention that if you can prove a certain entity property for this multiple Dirichlet series, you can do this higher moment. Although they also mentioned that there is a fleeting point between these 4 and 6. At some point, a little cause some difficulty, but it's also seems a good way to attack the question. Okay, so let me report some recent progress. Is that let's go back towards the smaller moment. Then like 5. Many years ago, recently, the Nathan, he proved that assuming a certain smooth tentative divisor conjecture, I will give you a conjecture in the case you are really interested in what it is. And he get all the main term with the error. Although there's a teeny tiny thing that he couldn't prove that the corresponding this big O the error to be half. There is something bigger than a half, but it's good enough to get this ornamental. And lately, during the COVID pandemic, and Nathan and Chen-Li and I, myself, we proved that we can do the S moment subject to the Riemann hypothesis. So the quick historical remark is that Harper, he showed that this one is correct upper bound, assuming the RH. On the other hand, Evans, he showed that if you assuming a certain form, the coordinate additive divisor conjecture, you can get this one is less than t to the 1 plus epsilon. It's predicted by the Lindelof hypothesis. So what we can do is that if you put these two together, you get asymptotic. Okay, so let me say a few words. Is that originally I was not going to do this, but Nathan said, okay, it should be easy. Just we can sort of be a copycat and to adapt his method to do this one. But there is at some points that the length of a Dirichlet polynomial we will discuss pretty soon that is a bit too long, and we have to sort of halfly abandon his result or method to do something new. What's new is that we need to use a sharp upper bound for the shifty moments of theta instead of like a traditional way, just rely on this additive divisor conjecture. And we only win by epsilon. So our method wasn't capable to do the lower term. And in fact, there is also the recent work concerning the use of the arithmetic to try to attack the tense moment. And I will say I will ask several times, and I thought about it. I think it's pretty hard to do so because our method, even for the S moment, we could not do anything longer to the longer Dirichlet form. For a tense moment, we will encounter something that quite lengthy. So okay. So for people's information is that naturally, if you open this integral and you will see something that this divisor sum, and we will need to use a certain smooth. At least f is smooth and the complete support function, and we need this one. And this one is for k equal to L equal to 2 is due to the Duke, Philander, and the Ivanich, and also refined laterly. And in fact, we obtained this conjecture by their delta method, also mentioned by another talk. It's this lab delta method. And in the same talk, there is a convolution sum. It's a tradition where it's corresponding to a modular analog, and this tradition on the additive divisor sum. Okay. So now let me say a few words about the shifting moments. It's in fact, we will keep grinding the information for the zeta over the critical line. So the natural question is that if we have a two case when we split into two parts and pull the two shifts, and these two shifts, alpha 1, alpha 2, they are the function of capital T. And then the natural question is, what will it look like? The answer is interesting in the following way. When these two shifts compared to log T, they are pretty close to each other, and they basically do nothing compared to the bond we know from the Harper, Roosevelt, Heath, and Sundararajan. And however, when this alpha 1 and alpha 2 are sort of far away, they will come to a picture that for the last case, you can see like right here. So the size of this growth rate or size of these shifting moments, they were shrinking. So in fact, this conjecture over chain D is based on the Keeling-Snasser random matrix model, and it predicts a correlation between the shift T zeta function. And then for us, it's pretty important. Is our first version of our paper article is assuming this conjecture, and we need something more for the last case. We need to do some upper bound, and on the other hand, for the lower bound, Trendy proved a lower bound by the Lutnick and Sadorjan's method. So this one is the best possible. So that is to answer the one question: is that can we do better for this conjecture to win more than epsilon? The answer is no, because this is the best bound we can hope in this direction. Okay, so. So myself, I'm not a super expert I'm not good at random matrices. So I also want to see why we have this correlation. And so at the very beginning, I told you that if we believe the set one, we believe the uniformity of the Seeberg central limit theorem, we have this case moment prediction. So we can do a similar thing for this shift T zeta. So in the case that let me show you that it's two results. According to the distance of alpha 1 and alpha 2, corresponding, everything take log corresponding to this log T. And when the first one, when they are pretty close, and we will see that close, so it will be okay. Well, then, so the first one was that these two random variables they are roughly the same in the sense of probability. And then for the second one, if there is everything take a log and there is a little log t, these two random variables we know about Selberg theory. This one is a normal 0, 1, normal 0, 1. They were apart to be independent. So what is interesting is that if they are not too close and not too far, and with compared to this log t, and if you put the correct constant right over there, and we will see that these two random variables in valid behavior like they are correlated. And then we can do this for the many shifty zeta. And for this one, you can see there is a name of Bogan and the Bohan and my names over there. There is a teeny tiny story I want to share. And this also I have learned from Professor Meli. We should be the scholar when we are doing the research. And so we should know the story about these things. And this is my lesson, how I have learned that. And I wasn't the expert in the area. So we proved this one, in fact, by we adapting the method of the Roosevelt-Santarajan in their proof of the Selberg theorem. And we do it for a general dedicated arrow function. So we can even do some delta king zeta function. And to answer the question asked by the Harper in the seminar Nicolapopaki, and where, for some mystery reason, we don't know why, Bogart's name was not there. And Bohan, I think he is a big fan of the Harper, so he was so excited to write a paper, email to the Harper. And after 3 days, he got an email saying, okay, dear Bohan, nice result. But unfortunately, this one was proved by, for the Riemann zeta case, it's proved by the Bogart. And he also showed us the title of the paper is this one. I even don't know how to correctly fluently pronounce these two words, and I even don't know what is the meaning for these two words. So what is really going on? The Bogart, he was studying the distribution of these zeros in light of or in spirit of the Selberg to prove his result. And this one is even not in the number series, it's in the probability theory and it's relative field. Okay, we learned something. So now that also back to our question is that trending she can also show that the upper bound. It's that basically she adapted the math of the Santarajan and she can prove this upper bound with many shifts. Again, the price is the epsilon right here. And we will see pretty soon that we really need to resolve her conjecture, complete the strength of her conjecture. And a quick remark, if we put all alpha I to be 0, and we recover the result of the Santarajan. So let me focus on give you some idea. At some point I realized it's a really lengthy paper. At some point I don't know, I will get lost while I was trying to do. So it's also the note for myself is what we were trying to do at this thing. So first thing to consider or study the S mode of the zeta, and we will use a smooth approximate functional equation to open it. So this you can see there's why there's a divisor function pop over there. And there's why the one reason why we need the additive divisor conjecture is that thinking about look at the inner term here. So the classical way to handle this one is that we consider distance of the n and little n to be little r. And so for each r, we consider the asymptotic of this one, and we take a sum. So in this way, for this back to the idea of the Hardy little word or eigen. And then, for example, if you consider to the D2, and you consider this one, you can this by the many the other including the Motohashi, you can deal with these things nicely. And so that's why we need the additive divisor conjecture. And so before we jump into the pretty difficult things, let me say a few words. Even from here, and if you assuming a super strong additive divisor, we cannot shut down the way. We cannot get it. The reason is that you can see the late phi is basically the smooth comparative support function. So this not a Dirichlet series, but a Dirichlet polynomial over a length like t to the 4. And if you integrate it, use a certain orthogonality, the error term put inside is roughly t to the 1 plus epsilon divided by 2. And then if you recall, the correct conjecture is like t log t to the 16. This one is too much for our purpose, so we cannot handle this one. So as we got stuck, and we were struggling for a couple of months, and then we find that, okay, we can adapt the method of Sandaraj, and we were so happy at that point. And that is their famous work and use on the second moment of the quadratic twist over the modular error function. So they are using a certain version, in fact, let's say the modular version of the Chen-Di's upper bound. They were able to, if you use this idea, they reduce the length of this corresponding the second moment of quadratic twist to a certain they can control. So basically, if you inject this the sharp upper bound, you can reduce the size by arbitrary saving of log. So in our scenario is that we use this one. You can reduce the length of the Dirichlet polynomial by arbitrary power of log, but with a fixed power. So let's say 100, you can put million or whatever. The problem is that if you keep grinding, and at some point you will introduce some error is slightly faster than arbitrary the power of log, and they will destroy again our argument. So we will get stuck again for several months. And at some point we realize, okay, if we remove that tiny epsilon, and magically during the process, we can reduce the length by power saving to the t to the fourth minus 2 epsilon. So you put it back, you can see that the length is there's only off, or the difference is this one and this one. They are just different by the epsilon, but it's one really safe already. Okay. And this requires sharp upper bounds of and it's why we can show that adapt the mass of the Harper, and we can prove this upper bound for more. Then the personal story is that, let me say a few words about. So you can see the Chen-Di proved manuscripts. There's a reason the current he was able to show that under RH enough to extend the previous mentioned result of Chen-Di. And also the Harvard student Sabo, he proved this one for the central value of Dirichlet error. In fact, this argument, the spirit can extend it to the journal, the error functions. We want to get upper bound. Okay, let me say a few words about this one. This one, in fact, is also is my personal story with Professor Murty. During the Professor Murty's conference, there is also this 2013, I think it's a Bahagava, it's the whole year long, there is so many events in the CRN. And there is one of these about entity number theory. Harper was there. And I was listening to what he was talking about his work. I was like, okay, this one is so complicated. And I'm going to do a long-range program, and I'm not going to do this. It is too lengthy. And I just like, okay, whatever. And at some point, the Nathan said, Peng-Jie, have you ever checked the Harper's paper? I just said, no, I don't want to do that, even for 10 years ago. And then, well, it turns out that, no, it's a destiny. If you are doing the math, sometimes you just cannot avoid certain things. So here is why I say it's complicated. Is that, or the Harper's idea is based on the idea of the Sandaraj. And this Sandaraj is based on one, there is a famous idea of the identity of the Sierberg is that you expand the log zeta, was the absolute value, to if you put all alpha equal to 0, you can get a nice upper bound. And then the reason why it's complicated is I was trying to do a representation theory with atomic one, and it looks too ugly. And even I don't want to read everything here, but I want to tell you that is that, in fact, if you put alpha 1, alpha 2 to 0, you can see this one in fact is sort of from the entity point of view, it's sort of relatively innocent Dirichlet polynomial. We know how to handle this one. Okay, and how about now we introduce the shifts? Is that at that point I was teaching calculus. So I learned this famous identity. Is that if you have two shifts, you can think Harper's the argument with the multiplicative structure. There's no way if you have these two. There's no nice cancellation. However, if you use this one, sort of luck with this rotation, so you can plane this one to the two shifts to arbitrary pair of the error functions. For sure, the current he used a more complicated argument to handle the general case. In fact, he put this into the study of the growth rate of zeta. So in fact, this is interesting to see if one can extend the current result to more general error function. Okay. And again, we know this upper bound, and what we want to do is exponentiate it, and we use this upper bound. So the brilliant idea of the idea of the Hopper is that you see now this one is no good because this one is not the correct point because it's exponential. You use a Taylor expansion. Its length is infinity. So we don't know how to integrate this one. Harvard said, okay, in fact, you can truncate this one, replace this by upper bound by the finite approximation. And every term here is relatively easy. And the next thing you do is just open it. And once you can detect the main term, we are done. So last thing I want to mention is how to detect the main term. Expect to how to detect the square. So this is the main diagonal term. So it's an idea of the Roosevelt. He proved this one and also adapted by Hopper. And then we need to slightly to include this thing because there is also the p square over there. We also failed to get Hopper. Okay. So I think basically I should stop right here. But let me say, everyone said what they have learned was learned from the Professor Murty. So I want to also share one is that it's back to 2012, the summer. After Professor Murty delivered his beautiful talk on the Lagrange program, arctic arrow function, the symmetry power arrow function. And he gave also a talk in the India philosophy and Buddhism. And at the end of the talk, his talk, he mentioned this lovely, beautiful thing. I know this one in the Mandarin Chinese, but I think that somewhat the English version is more prettier. And let me say this: how should one teach it to others without grasping to science, staying within the layer immovable? Why? Is that all conditional phenomena are like a dream, an illusion, a bubble, a shadow, like a dome, or like lightning. So probably we should discern it like this. Okay, so thank you, Professor Murty. And let me say a few words. I know that Apita and Francois, they could not be here, and Aksha also could not be here. So I am going to deliver this picture, is the idea of the city to Professor Murty. Thank you for all your guidance to help our students. Thank you very much.
Thank you, Peng-Jie. Any questions for Peng-Jie? Online participants, any questions? If not, let's thank Peng-Jie again.
Thank you. And happy birthday.
Hi, Aksha, are you online right now?